Okay, let's get started here today. You got my email, I suppose, yesterday explaining that we are going to go ahead and work with Bentley StormCAD starting on Friday and then also Monday of next week. And so I think you're logging in there. We can double check to see if Bentley StormCAD is installed on these lab computers, but I'm afraid that probably they're not. So I suggest that you put it on your laptop, and doing that would then give you also the flexibility to do your homework assignment with StormCAD and exam questions using StormCAD. And that's to your advantage, because once you figure out the basic functionality of StormCAD, then it's really a pleasure to use. It's agonizing to get installed and activated, but then once it's operational, it's really a great program to use. Jeffrey, do you have a question?
So we're going, if we have a homework problem related to the StormCAD, using StormCAD, we're going to turn it in the same way as the HY8 homework problems?
No, it won't just be screenshots. Homework 3 deals with StormCAD, and when we get into it, I'll give you specific instructions. All right. So homework number 2 is available right now on MU Online, and it's related to the rational method and stormwater, which we're covering in class today, as well as a spreadsheet technique for sizing pipes. Are there any other questions before we start talking about stormwater control? So you've just submitted homework number 1, which is the flumes and culverts, right? All right, so I'll get that graded in the next couple of days, and we'll just take it from there. So here's a couple of pictures that make an important point. You may see something similar to this depending on like your municipality. I don't think that I've seen these painted in the Huntington area, but the point is that the water that flows off of the road has to go somewhere, and it's pretty uncommon for the stormwater that runs off of the road to receive much treatment before it goes into a stream or a river or a lake. It usually, at the very most, would just have some very rudimentary settlement of grit, maybe removal of oil, but in a lot of cases it's just a pipe straight to the creek. And so since there's some important aquatic habitat that lives in the bodies that receive stormwater, there's occasionally these notices that people shouldn't pour antifreeze or oil or salts. There's a lot of things that can interfere with that habitat. So the water gets into the pipes from the road, and then it has to go somewhere. This is a photo of water that's coming out of a stormwater network and into a flow equalization pond. And the purpose of that pond is twofold. Number one, it's to reduce the peak flow rate that's getting into a stream, because if all of the pipes that's conveying water from roadways carries water to the stream when there's this burst of rainfall, if it all gets there very quickly, it can erode the stream and cause a lot of damage. And so it's good, number one, to reduce the peak flow, so you're kind of evening out the quantity that gets into the stream at any given time. But also by having a pond like this, where it's grass lined, it's going to encourage a little bit of passive treatment. So it's vegetative filtration, so that the sand that gets washed off of the road, or salts like I've mentioned before, or maybe oily grit, there is a little bit of reducing the harmful pollutant load before the runoff gets to the stream. And so if you look around, sometimes you can start to see what just maybe looks like a grassy area is actually meant to be a stormwater treatment and conveyance system. So the purpose of stormwater management systems is to, number one, preserve public safety, because having standing water in the roadway is really dangerous. The hydroplaning of vehicles means that they lose traction, and especially if it's just on one set of wheels. You've probably driven through puddles that's just on one side of the road before, and you'll notice that it kind of pulls your car into the curb. If you're not expecting it, you can lose control. So that's the first priority in stormwater management, is public safety. The other thing that you want to do in designing a stormwater management system, and it includes more than just the pipes and the gutters. The inlets have to be designed so that the water that's flowing in the gutters has enough opportunity to get down into the pipes, and so there's a certain system that we can use to size the length and width of the grates. Even they've gone so far as looking at the angle that the grates allow the water to flow into the catch basin. And so the next priority is trying to preserve the longevity of the network. And so if you reduce the velocity of water in a gutter, for instance, then that can help to prevent scour of the concrete gutter. Priority 3 is to get the water where it needs to be going, so natural or man-made drainage ways. And then a fourth priority, I guess you could say that this is kind of in ranked order from most important to least important, although, you know, it's debatable. It's a matter of opinion maybe that the environmental aspects are less important than the public safety aspects. But priority 4 is to, where possible, reduce the pollution that would be getting in. And then 5 is if you somehow have a way of integrating the detention into dual use, like if it could be a park when there isn't storm and there isn't excess rainwater. There are some places where they've built parks into, like at the mouth of a canyon most often. Like if there's a mountainous area and they have water that would be flowing out of a canyon and they route it through a park, then they could sometimes have multiple uses. So that's kind of like the top level view of what we're trying to achieve when we say stormwater management. We're trying to satisfy a bunch of competing stakeholders, and I guess priority 6 is to minimize costs, you know, to do all of this as cheaply as possible, because there are plenty of other things that need money. Here in Huntington, there are 3 different sewer systems. In Huntington, the majority of the city has what's called a combined sewer. There are some areas that have a separate standalone storm sewer that accepts only runoff from the roadway. But in a lot of the city, particularly in the older areas, the combined sewer accepts both wastewater flows and also surface runoff. And so a combined sewer is kind of problematic because occasionally during a really heavy storm, there's going to be more water entering the system than the hydraulic capacity can handle. And so that can mean a variety of things. It can mean that the combined wastewater backs up into people's homes. And that was a real problem that the city of Huntington had. I think it's probably less now than it was 10 years ago. When I first moved to Huntington, every year there would be people who would be getting a payout from the Huntington Sanitary Board because wastewater had backed into their basement. I think since then, Huntington Sanitary Board has done a better job of identifying the homes that are at risk and putting in like one-way flow valves so that wastewater can't back up into people's basements. And so there still are other problems, though. There's something called a combined sewer overflow. And so in the vicinity of Ritter Park, for instance, if you ever are over at Ritter Park the day after a storm, if you're walking along Four Pole Creek, you can kind of smell there's sewage in that creek. And so if the pipes don't have enough capacity to convey flow to the wastewater treatment plant, then they're designed specifically to discharge the water into the nearby creek. And according to EPA regulations, there's only a couple times per year they're allowed to have a combined sewer overflow. I mean, it would be better if it never happened at all, but there's so many old municipalities on the east coast of the United States that have inadequately sized combined sewers that it's inevitable occasionally on a rainy day the wastewater stormwater mix is going to get into the creek. So that's sometimes abbreviated as CSO, a combined sewer overflow. Jeffrey, did you have a question?
So is there a chance for the flow to back up through the storm drains themselves?
Well, if you think about the storm drains and where they're going, each of these homes would have a roof drain and a foundation drain. And so rather than having the stormwater from the roof go into the yard, which would be preferred, many of them have a pipe from the roof directly to this wastewater pipe. And so the sewage isn't going to make it up to the roof. It's just going to go like where's the lowest point of relief. So the lowest elevation where there's just empty space the sewage could go to. It's usually a basement. Occasionally it will get to the roadway, and a place where that happens here in the area is, maybe some of you know the Tanyard Station area, like on Route 60 by the new Aldi. I think there's a Longhorn Steakhouse and Sheetz over there. So they have occasionally a problem during wet weather. Sewage will come up to the roadway surface there, and that's another place where you can kind of smell it. If you're over at Aldi in the parking lot the day after it was raining, you can smell the sewage. And so that's evidence of a combined sewer overflow. And it should never happen, but from our standpoint, what we just have to be aware of is that when we have a combined sewer, there's a base flow of the wastewater, people flushing the toilets, running the shower, washing their dishes. That's going to be some of the water that's in these pipes. And then we're adding an additional load on top of that of the stormwater. And today I'm going to teach you the simplest way of understanding how much flow is wanting to get into the pipes. It's a simple model called the rational method that can allow you to analyze the network. And with Manning's equation to analyze the capacity of the pipe, and the rational method to analyze the flow that's going to occur, you can kind of see if one is greater than the other. Now, to do that, if you're doing the design, you have to know what are the local criteria, and every municipality can have different standards for what pipe sizes are acceptable and what slopes are acceptable and the materials that are in use. There are some really flat areas, for example, that maybe just because they have no choice would allow contractors to lay wastewater pipes at a slope that's relatively flat, and other places that have a little bit more relief, a greater elevation difference as the ground is sloping towards a river or the stream, or wherever the downstream receiving body is. If they've got more relief, then they wouldn't allow the slopes to be quite as flat, just because it's really challenging and you need a contractor with a lot of skill to lay a pipe out on a relatively shallow slope. It takes a lot more precision. The bedding that's underneath the pipe has to be more carefully placed if you're going to still achieve flow, but when it's relatively shallow slope. Of course, you need topographical data. You need information on the existing utilities and where the existing storm sewers are. And that's another point of real challenge, is that a lot of these storm sewers and combined sewers may be more than 100 years old, and they certainly predate the age of GPS coordinates and GIS systems and electronic surveys. And so integrating all the old paper maps into computerized systems has been a big task over the past decades, and we're kind of reaching a period of maturity here in Huntington finally, where I think probably better than 99% of the network is mapped here in Huntington, and probably cities of similar size. The utility information is easily available compared to how it was even just a decade ago. You need to know about where the streets are and the slopes of the streets, soil data to find compatibility with pipe materials and to identify concerns with maybe corrosive soils that would preclude certain materials like steel for storm sewers, or if you have clay soils, then you'd have to be aware of that in case there might be differential settlement or swelling. Understanding the water table is important and how that varies during the wet weather versus the dry weather in case there are pipe buoyancy issues. And then IDF curve, we'll talk about that in detail today. The abbreviation IDF stands for intensity, duration, frequency. And that's an important way of characterizing the rainfall. It's essentially for a certain area how much rainfall you expect to see for a certain duration storm and a certain return period, or the probability that a certain size storm will occur in a given year. So this is just kind of an overview of the typical data that would be needed to size a storm sewer. And the rules that a designer would follow, number one, is that if you don't have to use pumps and you don't have to use electricity, then as much as possible you're going to utilize gravity flow. And so we don't want to have all of the wastewater heading towards an uphill location. It's pretty obvious, but if you think about what that means, sometimes a pipe network can have a circuitous routing. You know, if you're getting from one part of town towards the other, you may have to go around a hillside to be able to get the entire system to flow by gravity. And so the length of the pipes would be greater than if you were taking a straight shot, but then you avoid the need for intermediate pumping stations and wet wells where the water is collected and then lifted and then flows downhill again. So this is a pretty important priority, achieving gravity flow in a drainage system. Commercially available circular pipe is the most common material that's used, and of the pipe materials that are used, concrete is by far predominant both in sewage and in stormwater. Yes, Jeffrey?
I believe like in New York and a few, or probably Huntington, that some of the sewer lines or storm drains are just brick layered.
Mm-hmm. Yeah.
So I think that's also, they can't replace it, so they just have to patch it up best they can, I believe.
Yeah, I think in big cities like New York, London, Paris, when they have brick sewers, it's really underground rivers. You know, rather than a circular pipe, it's more of like a vault system. Here in Huntington, where they do have old, like, vitrified clay pipes that may be cracking, what they sometimes can do is put a liner in those pipes, where it's not like they have to go down there and press the liner in, but there's a way of taking it inside out and like kind of blowing a liner into place using water or compressed air, kind of like think about inflating like one of those really long balloons that like a balloon guy would use to make a dog or whatever. So they have those balloons and they can put it on the inside of a cracked pipe and then it becomes watertight. So there are some ways to refurbish the old pipes. Sometimes they have to be completely removed. This third bullet point, using the smallest pipe diameter that will convey the flow that you expect, isn't just about economic optimization. It's also hydraulic optimization. And the reason is that if you have a relatively large pipe, a pipe that's too big for the flow that you expect to see, it's not good to have water flowing shallow through a large pipe. You know, if the pipe is too big compared to maybe for a certain flow rate, you could have had a smaller pipe. That's not that much smaller. If you had a smaller pipe, it was flowing more full. The problem with having shallow flow is that there is a long wetted perimeter. And so if you have a lot of wetted perimeter relative to the cross-sectional area, then the velocity is low. So the water is going to be moving more slowly. Compared to here, the velocity is relatively higher. So first of all, before I go any further, does everybody understand why the velocity would be low in a shallow flow pipe? And if you think about the friction is because of contact with the water and the pipe material. Here you just have more contact. We don't have this area in the middle where there's less resistance. So here you have more resistance, lower velocity. Now think about what's in stormwater and in wastewater in the case of a combined sewer. There are particles. It's not just H2O, but there's going to be sand and grit, gravel, glass, waste, debris, children's toys, garbage, Pepsi cups. There's going to be everything you can imagine in that sewer. And if the velocity is low, it settles to the bottom of the pipe. And so sediment can accumulate, and it's not self-cleansing. And so trying to have the smallest pipe diameter possible that will meet the standard helps to promote self-cleansing rather than a pipe that has a lot of trash and debris and sludge accumulating at the bottom of the pipe and then needs more maintenance. Then there are also considerations having to do with how deeply the pipe can be buried, like making sure that you're below the frost line so that the water inside doesn't freeze, distributing the loads above it by achieving the minimum cover specified by the company that produces the pipe, and so on. And minimum velocity is closely related to smallest pipe diameter. You know, with the smallest pipe diameter, it's easier to achieve the minimum velocities. But then there's also a maximum velocity where if you have a really steep town, then you have to be sensitive to the strength of the pipe and its probability of having hydraulic scour if you're set up on a really steep slope. So a place like Morgantown, where it's really hilly, they would maybe look at certain parts of the stormwater network and choose a pipe that's more resistant to scour. So maybe a plastic pipe instead of a concrete pipe in some of those really high slope areas to avoid scour of the pipe. It only makes sense, of course, that in a dendritic network where in a sewer what you've got is lots of branches that are all headed towards the same outlet. And so the pipes are going to be getting progressively larger. And so you have these small little lateral branches that are taking the wastewater to larger secondary pipes and then primary pipelines. And so you can't have it be getting smaller. Even if from a hydraulic standpoint, let's say that this one was really steep, and so it could be, in theory, a 6-inch diameter pipe, whereas the rest of these were 8. You wouldn't want to have that because there might be some basketball or debris, something in the 8-inch pipes that then would get stuck trying to get into a smaller pipe downstream. So it's because of debris and garbage collection concerns that the rule is established that the pipes only get bigger in the direction of flow. They don't get smaller as these tertiary and secondary networks are dumping into the primary pipelines. And also, no closed loops. You can have a closed loop in water distribution, and in fact there are some advantages to that. But in the case of wastewater, the water shouldn't face a branch and some of the flow goes one way and some of the flow goes the other. That's generally not allowed. It would just be that the water has only a single direction it can go, converging towards the downstream. All right, so here's a tabular summary of some of the rules of thumb as far as minimum and maximum velocity, typical pipe sizes in a storm sewer, the spacing of manholes that you'd want to see to make sure that there's easy access to pipe segments, and occasionally it'll be important to inspect and maintain storm sewers, and so the manholes allow cameras to get down in there, or they can put in pipes to send a huge surge of water to kind of flush everything out. So manhole spacing is important. At the bottom here, we've talked about a lot of this, but in the final hydraulic design, checking for surcharge means that you'd want to be aware of the slopes and the depths of pipes, because it's inevitable that there's going to be locations, you know, like the network's going to fail occasionally. There's going to be too much water getting in, and so you want to know, like, when there's too much water getting in, what's going to happen? How is the system going to fail? Are there going to be pipes that are under pressure and potentially a lot of pressure? You know, if you have a really hilly network and you've got steep pipes that are feeding into one pipe, then you have to know, well, the water's going to still be coming through those steep pipes. What's going to happen when it gets to the flat pipe? You know, is there going to be a manhole cover that explodes off of its foundation? I wonder if I've got easy access to this video, because I've got a really interesting video that shows a stormwater system failing. Let's see.
It's scary, or?
I'd be scared. Let's see if I've got this one. It might.
Kind of like on 5th Avenue, more often on like around CBS's on 26th Street, around there. That always like this massive overflow of water will usually pile up, and any car that are on the right lane and hits that water at a height of 35 miles per hour, it's going to smash your windshield. You can barely see anything.
I don't think this is the one I'm thinking of. Let's just see here. No, that's not it. All right, well, I'll find it. I've got a really fun video that shows basically a manhole cover exploding because the network upstream is continuing to feed flow into a pipe that no longer has capacity. All right, so I already showed you this picture of a neighborhood in Huntington that has both wastewater and stormwater coming into its combined sewer. Here's the basic idea of the rational method. This is a model. Remember, models can be a physical thing that substitutes for a greater reality and kind of simulates how it behaves, or it can be a concept or an equation. So the rational method is a model. It's an equation that predicts how reality behaves. And so it's a simplification of what you would observe in the real world. And the rational method says that you take some area and, like what's in that area is defined by geographic boundaries, like maybe roadways, like the curbs, or it could be elevations. This area is an area where all of the flow is going to be concentrating to a single point within that area. So if we go back just a step here, it may be that there's a curb along this road so that the water that's in the road goes immediately to a gutter. But on the other side, you've got this grassy area, these side roads, the roofs, and so you delineate a contributing area. Now I'm using some important technical language that you can find in that handout I gave you and we'll continue to use through the semester, but delineate means finding the continuous area that's all flowing towards the same outlet. So you delineate a contributing area for a watershed, and the units of that area maybe your square meters. It works out pretty nicely in traditional units, just as a matter of coincidence, that you can measure your area in acres, and then later on in the model we're going to get cubic feet per second. I'll show you how the units work out, but the first aspect of the model is just identifying a contributing area. The second part of it is picking a rainfall intensity that corresponds to the peak rainfall intensity that's relevant for that area. So this particular area, it looks like it's maybe, just guessed, estimating here, maybe 400 feet in height, and maybe this is 3,000, no, that's not 3,000 feet, maybe 1,500 feet wide. So to know the rainfall intensity that's applicable, you kind of have to know how quickly the water's flowing over the surface of the land. And that's a complicated idea that we will get into the details of it, but think of it this way. In the period of 1 minute, have you ever noticed in a storm when it first begins to rain, like for 1 minute maybe it's super intense, but then the rainfall slows down a little bit. There's this universal truth that something that has a high intensity just can't last for a long duration. Like think about your own capacity running on a track. You can run a 100 with a much higher intensity than you can run a 400. In the same way, like clouds stacking up vertically, just having this convergence of lots of cloud cover that would cause a really intense rainfall all at once, it's uncommon to have so much cloud density that you're going to have super high density for a long period of time, high intensity of rainfall. So if you have it rain for only 1 minute but high intensity, that may not be enough time for the water to flow towards the outlet. So there's this iterative relationship between rainfall intensity and the travel time within the watershed. So area and rainfall intensity so far. Any questions? The other aspect you have to understand is the runoff coefficient, the C value. Runoff coefficient you can think of as it's the percentage of the rainfall that would run over the surface instead of infiltrating into the soil or being retained at the surface. So it's how much is going to run off. It is a percentage, but it's expressed as a decimal. And then we use these three variables to predict the peak runoff, the highest runoff that you'll see during a storm, Q. So here's the equation. Q equals C, which is the runoff coefficient, I, which is the rainfall intensity, and A, which is the watershed contributing area. And You can get cubic meters per second out of this equation if you use the intensity is meters per second. More commonly, if you're looking at the way that rainfall intensity is reported, it would be millimeters per hour. And so if you converted in the SI system millimeters per hour into meters per hour, then what you'd get is the runoff would be cubic meters per hour. But in the traditional units, if you have acres for area, inches per hour for I, and then C is unitless, what you get is cubic feet per second. Pretty close. It's actually, I mean, to get it to work out exactly, there would be a correction factor of 1.008 that you'd multiply this formula by. But that's so close to 1 that most of the time that correction factor of 1.008 is omitted. And so you can get Q in cubic feet per second by multiplying inches per hour and acres. Now, this rational method is generally going to overestimate how much runoff you actually see from an urban area. And this method is most accurate for urban areas because it's in urban areas that we have the best hope of approximating a good C value. In rural areas, it's more difficult to have a consistent C value. So this is best for small catchments, and it's best for urban areas, but sometimes we'll use it for watersheds as large as 80 hectares, which is about, I think, close to 50 acres. So it's not going to be very accurate. It'll usually overestimate, but it's good to be conservative. So, given the choice of overestimating or underestimating, it's better to overestimate. So here's a visual representation of the assumptions. First of all, when you use the rational method, you're assuming a constant rainfall intensity when that's not realistic. In reality, rainfall intensity will be high for a little bit and then it'll taper off. And so that's part of the reason why this overestimates, is it's assuming a high rainfall intensity that isn't changing. And so the procedure that we'll follow when we use the rational method is, first of all, to estimate or calculate how long it takes for the water to travel over the surface. So back to this image. When we picked our contributing area, we said this is the area that all of the water goes to a single point. Like maybe down in the lower corner there's an inlet grate that receives all of the flow from this area. And a raindrop on this side wouldn't get to that grate. It's going somewhere else. And the rainfall here also isn't going down into this grate. But the boundaries of this contributing area just means that all of the rain that falls within these boundaries has the potential to aggregate at a single location. So once we have this area defined, we have to understand the travel time. Like a raindrop that falls right next to the grate would get into the grate within just a few seconds. But one that falls here, well, like what is the path it has to take and what will be the speed as it travels over that path? So water maybe would flow along the road for a little while, and then it would go down this way and get into the grate. And so you'd have to know the travel time. And you'd find the travel time that's the furthest away. And that furthest away travel time is the time of concentration that you use in the method, where you first of all know the time of concentration, and then you take it to an intensity, duration, frequency curve to find out what rainfall intensity should be used on the equation. So you delineate the area, you identify the applicable rainfall intensity, and then you compare the area to tables. And so you'd look at maybe an aerial photo, or you'd go to a site visit and you'd estimate, based on this area, you've got some trees, you've got some grass, roof, pavement, and you come up with a weighted average of the runoff ratio. And so the weighted average of the C value, and then you can finally solve for the flow, Q. Here are the tables that illustrate typical C values for different surfaces. So you can see like an asphalt versus a concrete roof, and the columns are corresponding to different return periods. And what you'll notice as the return period goes up, that's a bigger intensity storm. So there's a trend there. So think about the way that a concrete surface behaves during a 2-year storm versus a 25-year storm. What this trend is saying is that during a 2-year storm, 75% of the water that falls on a concrete surface will run off. And the other 25% will either be stuck to the surface, that's an abstraction, if it's just like wetting the surface but not flowing off, or maybe some minor infiltration through cracks in the concrete down into the soil. So that's during a 2-year storm. 75% of the water runs off. During a 25-year storm, 88% of the water runs off. So why do you suppose that the percentage of the water during the storm that runs off, why is it going up for a bigger storm? Pardon me? Okay, it is moving faster. That's true. That's only part of it. Okay, there's more rain in general. So if it takes a certain amount of water to wet the surface, like in the case of concrete, you have a sense that concrete is rough, and before the water is going to be running as a sheet over the surface of that concrete, it has to be wet. So if it takes 25% of a 2-year storm to wet that surface, then a 25-year storm is bigger. So it may be the same overall quantity of water is tied up as surface wetting, but since the overall absolute amount of rainfall is greater, then as a fraction, a larger percentage of the flow is running off. Okay, so what you can do is also look at the trend for slope. So think about grass. And they've got definitions for poor condition grass, fair, good condition. What is the trend when it comes to slope? How does that affect the amount of runoff versus how much infiltrates? How would you describe the trend for the effect of slope on infiltration?
Steeper the slope, the less infiltration.
Good, that's right. The steeper the slope, there's less infiltration. Or if we're putting it in terms of runoff, a steep slope increases the amount of runoff because there's less infiltration. So why do you suppose that is? Why do you suppose that a steep slope, like something that's over 7%, why is 40% of the water running off on a steep slope for good condition grass when only 25% is running off if it's flat?
Less room for pooling.
Okay, less room for pooling. Yeah, it's running over the surface rather than getting deeper and more hydrostatic pressure forcing it down through the soil grains and into the groundwater. So that's another trend that we need to be aware of. It's not just about how big the storm is, but it's also what is the water falling onto, and what's the slope of the ground, and then sometimes the quality of the vegetative cover. So there are a lot of different tables similar to this in textbooks and design manuals. Even state hydraulic handbooks may have different C values. And these decimals are referring to the percent of the water that runs off during a certain size storm. Okay, so I'd like you to get some practice with this. Consider a 5-year, 24-hour storm. So we would go to an intensity, duration, frequency table, and we'd find that the intensity is 95 millimeters per hour. And a certain catchment is 4 hectares of parking, 12 hectares of fair lawns on a 4% slope, and a certain amount of it is rail yard, and 18 hectares of single-family home. So what we sometimes have to do is look at what might these surfaces, what C value is applicable there. So let me just write on the board so that then we can go back to the table. What are the different surfaces we need to find C values for? So there is the parking, there's fair lawns. I think I have at best a fair lawn. Okay, a fair lawn, 4% slope. Rail yard, and then single family housing. All right, let's go back to the table and find some C values with this. Okay, oh, by the way, what's the return period of the storm? 5-year. Okay, so we're going to use the 5-year column, and for parking, 5-year, let's say it's asphalt parking. Okay, so the C value that we use there is 0.077. Okay, so C equals 0.77, and the area of the parking is 4 hectares. And the lawn, a 4% lawn, so fair, average slope, 5-year storm, 0.36. So C equals 0.36. Rail yard, now this is a guess. Like, think about what's in a rail yard. Maybe some bare soil, maybe some rocky areas. I'm just really guessing here, and I'm looking at different descriptions of things, you know, like a poor grassy area versus there might be some buildings in a rail yard. Let's just use a C value of 0.6. And, you know, that's not the right answer. That's just what I'm assuming. And so I'm going to put assume as a reminder to myself that you can go back later and change assumptions. If the answer you get seems unrealistic or if new information comes to light, you can update your assumptions later on. All right, now with housing, housing is going to be a mixture of grass and roof area. So we have roof area. For a 5-year storm, roof area would be 0.8, and grass is generally quite a bit lower than that. So again, let's just say a C value of 0.50, and that's also an assumption. Okay, but then the areas are important. So the area of the housing was 18 hectares, the area of the rail yard was 4 hectares, and the area of the lawns was also, it was 12 hectares. So we will come up with a weighted average, so a composite C value. And so the composite C is going to be 4 hectares of 0.77 plus 12 times 0.36 plus 4 times 0.60 plus 18 times 0.5, and then we would divide that by the sum of the areas. And in total, this entire area has 38 hectares of area. So then the composite weighted C value would be 0.495. Okay, so that gives us the C value that you can put into the rational method. All right, so do that. Let's go back to the formula for the rational method here. You've got the weighted C value. The intensity that you're going to apply is 95 millimeters per hour. And then the area of, the total area of 38 hectares. As a reminder, since probably it's been a while, 1 hectare is 10,000 meters squared. In other words, it's 100 meters by 100 meters. And so the 38 hectares that we have, that's 38 times 10,000 meters squared. All right, so find out what flow rate in terms of cubic meters per second do you anticipate to see coming off of this during the peak storm? Okay, we are running low on time, so let me show you the steps I followed to estimate Q. Now, already on the whiteboard, you've seen the calculating this composite C value. And the rail yard and the housing, you know, this isn't the only table you'll ever see of C values. You may find some that have even more, guesses and different types of land areas. But the point is that both the rail yard and the housing is going to be a mix of developed, which is high C value, and undeveloped, which is low C value type surfaces. So I came up with kind of a middle guess. And you'll notice what I'm assuming in the case of a rail yard is there's probably not as much grass in a rail yard as there is in single family housing. And so that's why the C value is lower for single family housing, is it's more grassy and less packed dirt, fewer buildings. All right, so once you have the composite C value, you just substitute it into Q equals CiA. So C is the composite runoff coefficient. The I, for us to get units of cubic meters per hour, since this is an SI problem, we have to have the I in terms of meters per hour. And then getting the amount of square meters, if there's 38 hectares and 10,000 square meters per hectare, then combining it all together in an hour for the peak flow, we'd see 17,860 cubic meters per hour. So then dividing that by 3,600, which is the number of seconds per hour, it's 4.96 cubic meters per second. Okay, so that's your first taste of the rational method. When we get together on Friday, what we're going to do is look at this example. Now, I guess I'll give you the handout now since I've got it and I don't want to forget to give it to you. We're going to use this template file that I mentioned in Excel. Here's a paper printout of it. What this spreadsheet will do is it'll allow us to identify for these three pipes. In this drawing, there's three pipes. There's pipe A, pipe B, and pipe C. And what we're going to ask for all of these is how big should the pipes be to take the water that's getting in at the inlet. So we'll go through kind of a step-by-step procedure that combines both the rational method, Q equals CiA, and also a formula that tells you the pipe size that's needed for a certain Q. So it's kind of like a back and forth method that will apply to all three pipes. All right, so on your schedule, bring your laptop to computer to class on Friday. I hope that we'll get a chance to try out Stormcat on Friday. And the next assignment is due on Monday. So that homework number 2 is available now if you want to get an advanced look at it. All right, I'll see you on Friday.